Okay, so population ecology part 1. Before we really start with population, let's review some terms right here on the board. Species, population, community, and ecosystem. So get out a sheet of paper or write on your notes somewhere the terms or the definition of these words. Okay, so species, population, community, and then I put ecosystem or biome. Okay, so species, you know what that word is. That's one organism. So I am one species. A species is just one organism. Yeah, just one organism. Species is just one organism. So like one bacteria is a species. One Miss Gilbert is a species. Okay, what is a population? A group of the same species. Right now we're trying to, today we're voting and you get to vote yes for the increased property tax or no is all I've heard about. No for property tax. Do what? Really vote at. Wherever you're registered to vote, like the city hall. But yes or no, because it's gonna make the cost of living and the I didn't go to any of the meetings, so I don't know. But it's supposed to better the population of trust falls. The population for who? Who's it supposed to better? People. It's not going to better the trees if we cut down trees and build a school. It's going to better people, right? And I'm not saying to vote yes or to not vote. I don't care. It doesn't matter to me. But I'm sure you and your parents discussed it and talked about it. Yes or no. We're voting yes for property tax. We're voting no for property tax. So we're really voting for new schools. Okay, so, but that's going to better the population, people. Not trees, not bacteria, not plants and algae. That's going to better for people. When I say that the world has over 6 billion people, I'm just talking about the population of people, right? If I said the world has 6 billion, a population of 6 billion, I'm talking about people. There's way more trees than 6 billion, right? Hopefully. Okay, so population is one species. All right, here's the $1 million question. What makes us the same species? Like all of us in this room are the same species. Girls and boys. All people are the same species. It doesn't matter what the race is, how tall, how short, what color your hair is. We're all the same species, so we're all one population. What makes us the same population? Our DNA is similar, right? Okay, well, we know that monkeys have similar DNA. So what makes them a different species? So some characteristics, you say? That's a good answer, but we like I could argue, you know, Savannah and I have different characteristics, but we're the same species.
They don't have the same. They have a different
Me and Savannah don't have the same DNA. We have different DNA.
but it's less similar.
So I'm so smart and she's not. I'm just kidding. But really. Okay, so I'm looking for a DNA is a right answer.
They code for different things.
DNA is a right answer. I'm looking for another answer. What'd you say? Number of chromosomes. I like that answer. Us and chimpanzees probably don't have the same number of chromosomes. I like that. So we're talking genetics. We're talking number of chromosomes. One more. Say it again. Yeah, but that's like a mutation. They're still the same species. Good thinking there. Logan's on it today. Come on, what makes us the same species and me and monkeys not?
Humans can reproduce, but humans and monkeys can't.
Boom, did y'all hear what she said? That was half word. Humans can reproduce. Me and a really short man of a different of a different race. I was trying to think. I was like, no. Anyway, a different race could reproduce. Yes. Me and a monkey could not. Like, it would not work. The chromosomes, when they lined up, they would not make an offspring. Okay, so a species has similar DNA, but they can reproduce together. I always think that dogs is a good example because, there's like all kinds of different dogs. There's like a pit bull and a Pomeranian and a Chihuahua and all the different kinds of dogs. Okay, well, dogs are all the same species. We have categorized them, but they're really all the same species because they can mate together. Like even a really big dog and a really small dog, it probably wouldn't work. It wouldn't work. But genetically, their chromosomes would line up and they would make an offspring. Like if we were to artificially inseminate the zygote. Okay, well, so the definition of a species, Josh brings up a good point. The definition of a species is that you can make an offspring.
Isn't it like a fertile offspring?
That you can make an offspring that can make an offspring, right? So you can make a fertile offspring. The definition of a species is that, or the same species, is that they can make a fertile offspring, or they can make an offspring that can have a child. So a horse and a donkey make a mule, and a mule is sterile. Mules can't have children. So to answer that question, horses and donkeys are different species. Good question.
It's like a cat and a dog, right? But the baby just wouldn't.
It wouldn't form a baby. Like they could go through the process of but it wouldn't work.
Yeah. But like a tiger and a lion and a liger
One time. Okay, so community, let's move on to the next one. Communities are all living things. Go back. Rewind. Does everybody understand population? Same species that can make a fertile offspring. AP Biology loves to ask that question on the exam. Okay, community, all living things. You got the cows, the ducks, the bacteria, the grass, the protists. So community is all the living things. And trustful, that would be the people and the trees and the grass and the bacteria and the mushrooms and my fish and my fish tank who are swimming nicely today. Notice they're all still alive. It's only been one day. Okay, and then ecosystem, what's that? You should know. Living and non-living things. Good. So the living and the non-living things. I'm sorry? You're right. So you're talking the animals and the plants and the nitrogen and the water and things like that. Okay, so let's talk about this like a farm real quick, and I'll give you one more example and we'll be done. Okay, so the species is the farmer. There's one of them. Species, one organism. The population is the population of cows on the farm. One group of cows, like maybe there's 15 cows on the farm. Okay, the community is going to be the cows and the ducks and the grass and the birds, all the living things. And then the ecosystem is going to be the soil. Soil is non-living. The nitrogen in the soil, plus all the animals and the rocks and the water and the farmer. Right, so the ecosystem is all of it. Okay, so looking at your notes with me, it says that a population, it says same on B. A population is the same species, same time, same place, and showing signs of reproduction. A squirrel in Alabama and a squirrel in Georgia could reproduce together, but they're so far apart they can't. So a population is the same group of organisms interbreeding. So they could show signs of reproduction. Okay, the human population, here's a picture, will soon be over 7 billion. So do you see how the graph started out with low numbers and then now it is exceeding exponentially? Do you know what exponentially means? It's doubling. Exponential means like it's doubling. Like an exponent is like a square, right? You're multiplying and multiplying and multiplying it together. So exponentially it's growing. Okay, it mainly focuses on density, population. Like have y'all ever heard of a census?
Yeah.
I think it's every 10 years. The government sends a paper to your house, and your person in your house has to fill out how many people live in that household. And it's important that you're accurate and you send it back. So that's important. Okay, and then, so here's just a picture of a really populated area.
This spring break?
Obviously so. Okay, mark recapture method. Okay, this is a formula to show how many people or what is the number of that population. So in this picture you can see the people are looking for something, but it would be like, okay, we captured all these fish, for example, and you mark them somehow. So either like tag them, like, you've seen cows that have tags in their ears. Something like that, like tag them or mark them, and then you release them. So the first time you get them all and you mark them, and then you release them all. Okay, and then the second time you come and you capture them all, capture a whole bunch again, and you look at the number that are marked that you got the second time. Does that make sense? So let's think about squirrels, because we can, let's say we set up these traps and we caught a bunch of squirrels. Let's say we caught 25 squirrels and we put a little tag in their ear and we let them go. Okay, well then the next day we set up the cage again, and this time we got 25 squirrels again. Some of them had tags and some of them didn't. Some of them were the ones we originally caught, and some of them weren't. Does that make sense? Okay, so that formula there is how you would determine, is someone's formula that they made to help determine the population. So it says the number captured and marked in the first group, so that first 25, times, let's say in the second group there were 15 of them marked. So times 15 divided by the number recaptured, so we said 25. We captured 25 both times. And that'll give you an estimated population size. Okay, if I ask you to determine, you know this answer, come on. If I ask you to determine species richness in a population, how would you do that? Count the number of species, right? Did everybody hear what she said? Count the number of species. Okay, Alex, how would you determine species diversity? Species diversity. Somebody help them out. You would have to count them and get a percentage of them, right? Because species diversity is the abundance of each one. All right, are we clear on those terms? Okay, different types of dispersal patterns. So organisms live in different types of patterns. Okay, so dispersal patterns that are clumps would be like fish. Or what else lives in clumps? She said humans. You think humans are clumped? Yeah, think about it. Humans are clumped like in Atlanta. There's like a clumped area. And like New York and really populated areas. I really think that humans are clumped and trustful. Like we're all clumped right here. And then there's not as many people that live in Springville and Asheville. Right? But in Birmingham and Trustful, it's like really clumped. Okay. Anything else? Come on. Think of some type of animal that lives clumped. What'd you say? Ants. Ooh, good one. Because they all live in their little houses. It's like clump. What'd you say, Josh? Ant houses? What is it? Meerkats? Prairie dogs. Yeah, wolves. Good. Okay, the next one is be uniform. And the textbook gives an example of penguins. I guess they live not too close, but not too far away. I always think of uniform, and I don't know if this is a good example, but corn is always planted in rows. So it doesn't grow naturally uniform, but every time I've ever seen corn, it was in rows. Right, so corn is in rows. Right, so that's just the example I always think of. Probably not a very good one, but so uniform. This is territorially. I got this picture right here I got off the internet. It's a type of flower that releases a poison, and so no flowers or plants grow close to it. So it's like it makes a little radius around itself that you can't grow that close to it. So that was just an example I found. Do you see it where it says it releases a chemical which inhibits growing right next to it? Okay, so that was uniform. Let's go with random. Organisms that are random. No apparent pattern. And the example in the book, this is a picture out of the book, so trees is their example. Can you think of anything else? It's random. Where would bacteria fall? Do what? Everywhere. I think that bacteria would be, this is just my opinion, I think it'd be clumped. Because it does binary fission, right? So it's like over in that one area. That's what I think, I don't know. The clumps may be random. Maybe that's a different topic. Okay, so think of some more animals. And what about bees? How do you think they live? Like bumblebees? Clumps for sure, because they live in their houses. Squirrels. I think squirrels are pretty random, because they don't live like in packs. They live in wherever the woods are. Okay.
Because random would be like they can live anywhere, but they only live in the woods.
Well, uniform I think is more like there's a pattern to where they are.
Would that not be the woods?
No, but they're like all randomly spread out through the woods. But I see what you're saying. She's saying that the woods are actually uniform. Does that make sense? Makes sense to me? Okay, so let's look at this. So this is really common sense. How are we going to increase the population? 2 ways. Births and... No, increase population. Come on. People moving in. Like if the city of Trussville is growing because offsprings are being born and people are moving into it. And moving in immigration with an I. Okay, how are we going to decrease the population? Deaths and immigration with an E. You can remember those 2 words because immigration with an E is like exit. Immigration with an I is like moving inward. Okay, so I like inward, E like exit. Okay, so we're going to increase the population. I've seen biology teachers that do this newspaper project, and they make all the kids bring in newspapers, and they do the number, and they try to see if the population in their city is growing or getting smaller, and they do the births minus the deaths, and they just look at births and death rates. But that doesn't work because the Birmingham paper doesn't necessarily have all the birth announcements and all the death announcements. Like in order to put your newborn baby's birth announcement in the paper, you have to pay. You have to pay to have the article. Like a birth announcement with a little cute picture of your baby. I don't know. And then again, to do a death announcement, like to put the funeral arrangements, you have to pay for that. So it didn't really work for us the time we tried it. The birth announcements and the death announcements. And I think birth announcements were only on Sunday's papers. So it didn't really work for us. But you can kind of see if every day there was a birth announcements page and a death announcements page, how we could calculate whether Trussville was growing or getting smaller. Yes? Okay. So we got growth, we got decline, and this is a life table. So it shows, this is about squirrels. Okay, the first column is the age, so 0 to 1 years old. And it says that there's 337 alive at the start of the year. Okay, well, the start of 1 to 2, there's only 252. What happened to them? Some of them died when they were babies. Okay? And then it shows number of deaths during the year, 207. Death rate, 0.6. Okay, so the death rate, do y'all see how it's really high? Or it's 0.6, it's higher from 0 to 1. So some of them might not make it out of being an infant squirrel. Right, like they die as an infant. But then it looks like if you can live to 2, your chances of survival increase. So it's like 0.6 0.5, and then 0.4, 0.4, 0.4, back to 0.5. So it's like if you can live past 1, your chances of survival increase. But then do you see where if you get to, 7 and 8, your chances of survival are 0.2. So that's like huge. If you live to be 7 and 8, you're probably not going to die. You're a smart squirrel that can hide from predators. But look right here. The next one is 0.75. So if you're a squirrel and you live to be 8 or 9, your chances of dying are 75%. Why? Because you're old. You're an old squirrel. Right? So can you kind of see, you don't need to know these numbers, but can you kind of see how to read it? And then average life expectancy. And this is the last column. Okay, so, and that's females versus males. It looks like, which one lives longer, females or males? Boys are not smart, even in squirrels. They don't know how to hide from the predators. Just kidding. Okay, survivorship curve. This is the most important part of today. So what I want you to do is draw this graph on your paper beside your notes. And label it. You don't have to draw the person, squirrel, and clam, but label it 1, 2, 3. Yes, you definitely want to have a title on this graph, and you need to label your axis, because that hurts some of you on your biome project. Do what? Yeah, unless your project was really creative, then I didn't take off. So draw that. Okay, 1. Somebody tell me what happens at 1. Oh, y'all want to finish drawing, then I'll talk. Okay. Between the fish tank going and the fan going, like, I'm having a hard time paying attention. My attention deficit disorder is killing me. Okay, so let's talk about these. Number 1, what's happening on number 1? Number 1, increase and then decrease? No. Look at Roman number 1, the person. The population size. Look at it. We're talking about the number of survivors. Yeah, it's the same until looks like 50. And then it starts to decrease. So most of the time, people, or organisms with survivorship curve 1, the babies live to be really old, and then they die off of old age. Does everybody see that on 1? Okay, what would you say about 2? Birth rate, death rate, same. For every one that's born, 1 dies. Born, dies. Born, dies. So the population is steadily decreasing. Okay? What about 3?
What is that?
That's like a clam or something that lives in the ocean. Like a crab and a seashell.
A lot of die, but not
A lot die, like right off the bat. And then it looks like 1 lives to be 100. Do y'all see the difference in the 3 curves? Okay, so let's go back to curve 1. And the example given is people, but what would you say about the life of these people, of these organisms? Think about yesterday's notes. Do what? Yeah, they survive for a long time. So what is their reproduction style like? Like polygamy, monogamy, monogamy, right? It would be 1. What do you think? So they have lots of parental care or no parental care? Lots of parental care. So there's not many offspring born, but the offspring live, so there's a high chance of survival. Okay, and then with 2, the number of survivors, and then so it's like how many survivors versus how long they're going to live. Okay, or percent of maximum lifespan. So half of them live to be 100, or some of them live to be 100, and some of them don't. So it's like born, die, born, die, born, die. The percent of maximum lifespan is not proportional, right? Okay, and then look at 3. There's a whole bunch of babies born, and then boom, they're gone. And only 1 or 2 lives for a full lifespan. Example of Nemo, right? All those babies are born, and then they all die, and 1 lived. And his name was Nemo, and he had a short fin, right? Okay, so 3, you would say not a lot of parental care. Polygamy. Okay, and then it talks about environment. So 1 is probably in a favorable environment, and 3 is probably in a harsh environment. Do y'all see those? Take a second and look at what's on your notes and look at the graph. This is the most important part of today. Survivorship curves. Okay, and then here's a reproductive table. This is, again, squirrels. But, it shows the first column is years. The second column, proportion of females, like having a baby, having offspring. Okay, mean size, sorry. The mean size, whether it's girls or boys, like the average size. And then just girls and then just boys. Okay, so you're not going to have to memorize these pictures or anything like that. You're going to have to answer questions based off of them. Okay, so Josh, looking at this, when would a squirrel have the largest amount of offspring? Looking at, like, what age? When would a squirrel have the largest amount of offspring? Yeah, 5 and 6. Do you see how the average number of offspring is 4. Oh, no. It's actually 5.45 if you look at. So it'd be 4 to 5. Y'all see that? So the average number of offspring is 5.45 for squirrels that are aged 4 and 5. Look at it. Right, so if the question asks when are they going to have the most offspring, the answer would be 4 and 5. Do y'all see that? So you're going to have to answer questions based off these things. Okay? It really looks like it's half girls, half boys. Especially like at 9 and 10 it's the same. At 8 and 9 it's the same. At 4 and 5 looks like it's more girls. So 3, 4, and 5 it looks like there's more girls. Is there ever a time when there's more boys? It doesn't look like it. Okay, so hopefully you can kind of read that. Are there questions on these? One time I was taking this is just a funny story. One time I was taking an ecology class in college. Like, I took a class in college that was just ecology. And one day, instead of having class, we had to go to the cemetery and make a life table. And we had to walk around, and every person in the class had to get look at 100 tombstones and write down whether it was male or female. And I want to say we had to do that based off the name, like what the person's name was. How long they lived, so birth and death, how long they lived, and we had to graph it. And then we had to go back to the room and graph it. So when we went back to the campus and graphed it, on my graph was different than everybody else's, of course. On my graph, it was like I had a few children that had died, so not many, which was normal, but a few children, and then I had a large peak of children or of people that had died that were like age 25 to 35, males. And then Like it was like 45, 55 was low, and then, you know, around 65 and 75 it increased. So the 65, 75 was because of old age. I understood that. And, you know, the children was probably just accidents that had happened. I understood that. But we had to write a paragraph, answer these questions on why our graph looked the way it did. And my graph didn't look, nobody else has had that large peak where it was 25 and 35, and I couldn't understand why. And it was based off, we had to do it based off years, like what year they had died. It was like a lot of 25 and 35-year-old men had died in that particular set of years. And so I went to the teacher and I was like, I don't know how to answer these questions. I need help. I don't know what my answers are. And he told me that there was a part of the cemetery that was for people who had fought in war. And I had been in that part. I was like, man. So anyway, I just thought that was kind of a funny story. I couldn't answer my questions, and that was why. Okay, grab your sheet of paper. Put your notes away, please. Notes away. Sheet of paper.